Okay, so what we've done is we've talked about standing waves that are formed on transverse standing waves, sorry. So you make those with a transverse wave, like a rope. Now what we're going to do is we're going to do the more difficult case. We're going to do standing sound waves in air columns. So these are longitudinal waves, right? Sound waves are longitudinal waves. So very, very different than a nice rope transverse wave, you know? Okay, so here you go. So this is a sound wave. How do you make a sound wave with a speaker? If you have a speaker at home, like, you know, old-fashioned big speakers, you take the cover off. All you're going to see is that it just goes back and forth, back and forth, back and forth, you know? And so this is how it works. So the speaker goes back and forth, back and forth. So this loudspeaker cone moves back and forth, creating regions of higher and lower pressure. That's the big deal, pressure. So high pressure compression, low pressure rarefaction. Okay? So again, just imagine all these air molecules, you know? So here's a compression, a lot of pressure. Here's a rarefaction, hardly any pressure, and a lot of pressure, you know, and so forth and so on. So there's a pressure. So this is pressure versus position. And here's atmospheric pressure. So you can see where there's a compression, the pressure is greater than atmospheric pressure. When there's a rarefaction, the pressure is less than atmospheric pressure, right? So obviously that's max pressure, min pressure, max pressure, min pressure. And you get a wavelength. So the sound wave is a pressure wave. Compressions are crests, maxes. Rarefactions are troughs, mins. All right. So here is just, there's not a wave. It's just air, you know? So uniform pressure, no displacement, you know, just the molecules just sitting there, right? You know, minding their own business, okay? Now, what we're going to see, so we're going to discuss each of these three cases. This is called an open air tube. This is open-closed. This is closed-closed. So what we're going to see is that for each of these columns, you know, there's a pressure wave, right? And it's going to get to a discontinuity, right? There's going to be a discontinuity. And where there's a discontinuity, again, some of the wave's going to be transmitted, some is going to be reflected. And it's the reflections, you know, just like with a transverse wave or a string, that cause the standing waves. Okay? All right, so let's do it. Let's do the open. All right. And you better pay attention because you're going to have to do this in lab if you haven't already done it. And you're going to have to do it in your exams, including the final, and you have to figure out the formulas. But it's not so bad if you understand it, you know? Okay, so what's the pressure here and here? Well, atmospheric, right? Atmospheric, no kidding. So, and you know, it's not going to change, right? I mean, it's open, right? This is open to the atmosphere. So this is always going to be atmospheric. It's always going to be atmospheric, okay? So, therefore, if it doesn't change, is it a pressure node or antinode? Well, node means no oscillations, no change, right? So those are pressure nodes, okay? All right, now, this is the key. I mean, you think physics is hard? All you're doing is drawing pictures. I promise you. All you're doing is drawing pictures. All right, you have to have nodes. Node. And then all you do is draw the different possibilities. All right, that's all you're doing. So, I mean, think about it. I mean, the number, this, you know, the first possibility is just this, right? Node, you know, node. And then what else can you do? What's the next possibility? Well, you just get, you know, like that, right? What's the next possibility? Okay, so you have one of these things, and two, and then three. That's all. I mean, honestly, that's all there is to it. Just draw the possibilities, making sure you have nodes at each end. That's all. Okay? All right, so now let's think about it. So here's the length of the air column, right? And so the length of the air column? Well, the first one, again, remember, this is a wavelength, right? That's a complete wavelength, right? And so, or you can think of it like this if you want, I don't care, right? Make it a standing wave, pretty sad looking one. All right, so what is this? That's this part, so it's a half a wavelength, right? It's a half a wavelength. So L is a half a wavelength, okay? Now what's this? Well, that's a complete wavelength, or let's say it's 2 half wavelengths. So it's 2 half wavelengths. Okay, and what's this? It's 1.5 wavelengths, so it's 1, 2, 3, 3 halves. So we have 3 half wavelengths. There, let's be ridiculous about it, huh? All right, so we're going to do the same thing we did before with an index, you know, index. So we're going to say L, the length of the air column, equals a number M, 1, 2, 3, 4, 5, and da 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 da, lambda over 2, all right? That's cool. And, all right, so now solve for lambda. So therefore, lambda, might as well give a little index right there, subscript. So lambda M is 2L over M. I got to say what M is. By the way, M is not always going to be 1, 2, 3. We'll see that in a minute. So you got to be careful, all right? So then we have, you know, just like last time, V equals F lambda. So lambda equals V over F. So then we say, so therefore, we say 2L over M equals V over frequency. Then we flip it, and then we get F over V equals M over 2L. Then we get rid of the V. We just want F. So therefore, F, put a little subscript, equals M times 2V, oops, sorry, V over 2L. Ta-da! Where M is this. And, I mean, that's all there is to it. All there is to it. Okay, so there you go. So those are the only frequencies you're going to get for open-open. Well, it means you're going to get, these are called harmonics. So you can get odd harmonics and even harmonics. All right? So those are the frequencies that make a standing wave in an open-open. And hey, where have you seen that before? Standing transverse wave, right? So that's cool. All right. Now, let's do another one. Okay, so this is a closed. All right? Closed. And you should be able to do this on your own, but I'm going to do it, but you should follow along, make sure you understand it. All right, now think about it. You have this, you know, the air is moving, right? You're getting a sound wave. What's the pressure here? What's the pressure here? It's not atmospheric anymore, right? It's going to be either max or min. Agree? Because the air is, you know, the air is going like that. All right? So is it going to be a pressure node or antinode? It's certainly not going to be a node, right? Node would be no change, no oscillation. But here, it depends if it's a compression or a refraction, it's going to be max or min. So it's a pressure antinode, okay? All right, now wait a second. What's between two pressure antinodes? A pressure node, right? A pressure node. All right, so you just draw the possibilities. Okay, so again, I shouldn't show you. So just draw the possibilities. Okay, you want an antinode here, and a node here. What's the only way you're going to do it? So, all right, there you go. All right, so that's the first one. How about the next possibility? Well, wow. So just try fitting waves in here. I mean, you don't have to do a lot of thinking, just fit. So, and I don't, you know, I'm not an artist, so I'm not really super careful, right? And then it's just going to be, let's see. I forgot. I got to cheat. Wait a minute. No. Ah. Yeah, I wasn't right. That's right. Okay, what can you fit between this and this? I mean, the only thing you can fit is something like that, right? I mean, right? Let's do the third one. Oh gosh, so anti, anti. Now what can you fit? Just two of these guys, right? So, oh gosh, that's pretty bad. So this is what I'm trying to say. Okay, so all I'm saying is you get an anti-node at each end, and you just fit waves, you know? I mean, that's all you can do. Make sure you understand that. Drawing these silly pictures is the key. I'm not kidding. So that's really it, all right? Okay, so let's do what we did last time. It's the same old, same old. So L, okay, let's see now. What's this? That's not a, it's a fourth of a wavelength, right? It's a fourth. So I have 2/4, which is a half. So I have lambda over 2. Okay, what's this? This is a half. That's a fourth. That's a fourth. So I have a half and half. So I have a, so what is it? It's a 1, right? So in other words, this is a half. This is a half. So I have 2 halves. Okay, what's this? Half and a half, and then another half. So it's 3 halves. No kidding. You see the pattern, right? And so forth. Okay? Now, what I'd like you to pause your video and you figure out the rest, right? So you do what I did and figure out the frequency. So pause your video. You have to do this. You're going to do this on your homework, on your lab, and in your exams. You have to do it. I'm not going to give this to you, right? So pause your videos and do it. All right, so I assume that you've figured it out, but let's just do it anyway. So we have L equals m lambda over 2, where m equals 1, 2, 3, okay? And solve for lambda. So lambda equals 2L over m. And then again, V equals F lambda. So lambda equals V over F. So this equals V over F. Then you flip it, you get F over V equals M over 2L multiplied by V. And there you go, right? So there, so you can write that as M V over 2L. All right, so there you go, right? Okay, all right. So that's closed, closed. Now let's do the hard one. Let's do the hard one, open, closed. All right. What is the pressure here? Atmospheric, so it's a pressure node. What is the pressure here? Well, it goes between min and max. So the pressure antinode, right? So let's do it. So you want this to be a pressure node, right? You want this to be a pressure antinode. So you got to admit something like that, right? And then you just keep doing it, all right? So anti-node, node. So you do this, and then you got to figure out, okay, what's my next possible one? I mean, what can I do for my next one, you know? This has to be open. This has to be this has to be anti, this has to be a node. So the only possible thing you can do is what it's shown, right? So you do this, and you do one of these, right? So it's anti-node, node. And then for the other one, you just do that, because you can't get anything else. You can't get anything else to fit. So make sure you totally understand these drawings. It's the key, honestly. Nothing to memorize, just draw pictures. All right, now let's do the, well, okay, so pause your video. Please do this. Pause your video and figure out the frequency. All right, so I assume you've paused your video and you're back. Let's do it. Okay, this is open, closed, right? Yeah. All right, so, okay, now how much of a wavelength is this? This is a fourth. So I have L equals lambda over 4. Okay, what is this? Well, this is a half. This is a fourth, so it's 3/4. So it's 3 lambda over 4. what is this? A half and a half and a fourth. That's 5/4. So it's 5 lambda over 4. Okay? So I can just say that L equals m lambda over 4. But now I got to be careful. What's m? Now m is just 1, 3, 5, right? It's just odd, right? It's just odd. Okay, now you just do what we always do. So lambda m equals 4L over m. Okay, v equals f lambda. So lambda equals v over f. So this equals v over f. Flip it. So you get f over v equals m over 4L multiplied by v. And make it look nice. So you get f m equals m v over 4L. But again, that's the thing, right? Only odd harmonics. So with the open close, you're only going to get odd harmonics. Right? Odd harmonics. All right, let's talk about wave interference. Wave interference. So we have two sources, okay? Two sources. And we want to discuss this. Now we want to say that the speakers are completely identical. So what's the only difference between the sound waves reaching the listener from this guy and this guy? What's the only difference? How far the sound wave has traveled, right? Right? I mean, you know, this one travels further than this one. This one travels further than this one. So the only difference is the distance traveled. That's called path length. Path length. Okay, now think about it. What kind of interference you're going to get if the path length is one wavelength? Well, that's just going to be constructive, agree? Because, you know, a wavelength doesn't really do anything, right? So it's going to be constructive. So that's called in phase. Okay? And here's a great picture of it. So here's the path difference. It's one wavelength. So you can see that. See how they just constructively interfere everywhere? So if the path length difference is a wavelength, constructive interference. That's called in phase. All right? Now how do you get to destructive? What do you think? Well, if the path length difference is lambda over 2, right? So look, now the path length difference is lambda over 2. So what do you notice? What kind of interference is that going to be? Destructive, right? Destructive. That's called out of phase. We're going to use that a lot next semester, all right? Okay, so if you have identical speakers, the type of interference depends on the path length difference, okay? The difference in the distances traveled. Okay, let's do some, all right, now, if you want constructive, so this is the path difference, delta D. If you want constructive interference, if the difference in the distances traveled is m lambda, it's always going to constructively interfere. If the path difference is half a wavelength, or 3 halves, or 5 halves, right? That's why I put this m plus a half, right? Because you get 1 half, 3 halves, 5 halves, whatever. If this is equal to that, you're always going to get destructive. So this is in phase, out of phase. Okay? All right. 2 rays of light reflect from glass surfaces separated by 150 nanometers. What's the path length difference? So pause your video and figure it out. Okay, so you're back. So this one travels this and this, right? This way and then that way. So this one travels 300 nanometers more than that one. So therefore, the path difference is 300 nanometers. Okay? Here. 2 identical speakers, 1.5 meters apart. Both speakers are identical. What kind of interference do you have right here? Now, this is halfway between. So this distance is exactly equal to that distance. So that means that there is no path difference. So, and the speakers are identical, so what are you going to get? Constructive interference, right? All right, let's see. That makes sense. No path difference. Okay, this is tougher. Now we want to get the interference at B. All right, so what's the path length difference? Well, it's 1.5 meters, right? This guy goes from here to here. This guy goes, this one travels 1.5 meters more than this guy, okay? All right, so we know the path length difference is 1.5 meters. But, all right, but now we got to figure out, is this a half a wavelength? Is it a wavelength? What is it? Well, F equals ma, right? So V equals F lambda. Now they give us that velocity is 343, so 343 meters per second. The frequency, isn't it nice? 343 meters per second. 1/second. Hertz. And so what's the wavelength? 1 meter, right? All right, so the lambda is 1.0 meters. Now, what's the path length difference? The path length difference is 1.5 meters. So that's 3/2 of a wavelength. That's destructive. That's destructive. All right? Okay? We'll do one more, I think. All right. Okay, now we want to do point C. Now see if you remember your trig. All right, so this guy, that's his path length. This one, that's the path length. All right? So let me draw that. Okay, so here's C. So this is 2 meters. This is not scale drawn. This is 1.5 meters. And then that. All right? So, trig. This is a 3, 4, 5 triangle, right? This is a 3, 4, 5 triangle. This is 3 times 0.5. This is 4 times 0.5. So this is 5 times 0.5. So it's 2.5. 2.5 meters. If you don't know what I'm talking about, just figure out the length of this using the Pythagorean theorem, okay? It doesn't really matter. All right, so this one goes 2 meters. This one goes 2.5 meters. So what's the difference? What's the path length difference? It's 1/2 meter, right? It's 1/2 meter. Well, we already figured out that the wavelength is 1 meter. So if the path length difference is 1/2 meter, what are we going to get? Destructive interference. Do you have 5 minutes or you want to quit? Okay. All right, okay. Thank you. All right, last topic. Beats. Beats. All right? Okay, so have you ever gone to a concert and you have a bunch of violinists and before they perform, they kind of, do their thing? What are they doing? They're trying to make sure everybody is in tune, And so they're trying to make sure that everybody has exactly the same frequency. So let's say you have 2 violinists and their frequencies are just a little bit different, So what are you going to hear? You're going to hear something like this. Wow, 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 wow. All right, something like that. Okay? And so there's a certain frequency to that, right? But it varies in loudness, right? Wow, 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 okay? So that's the beat frequency. That's the beat frequency. So this is what I'm talking about. So here you have, so there's 2 waves, right? And you can see that they're just a little bit off. So here, they're sort of kind of constructively interfering. Here they're destructively for sure, and here they're more constructively again, So you hear this loud, not loud, loud, not loud, loud. That's what you hear, okay? All right, so this is the beat frequency. So it's the absolute value of the difference in beats. So if you have one, I'm just making up something. So if you have one violinist playing, I don't know, give me 111 hertz, and the other violinist 112 hertz, the beat frequency would be 1 hertz. because you just subtract them. Okay? All right, now, if this works, it'll be a miracle. Okay, there's a YouTube, then we're done. All right, let's go. Okay. All right, so I hope you could hear that. I mean, you know, he played one tuning fork, then he played the other tuning fork, and they were real similar, but they were different. And then he played them both at the same time. You just hear this kind of thing. Okay, let's review. So superposition means you're adding waves. That's all you're doing, adding. Standing waves are generated. We talked about that. You have a traveling wave going this way, reflects, goes that way, reflects, and at certain frequencies only, you get a standing wave. We calculated the wavelengths and the frequencies for standing waves on strings and sound waves and tubes, and you have to know how to do that from scratch. We talked about constructive, destructive interference. And we talked about beat frequencies. So, I mean, there it is. There's a chapter, you know. This is true for any wave. Velocity equals frequency times wavelength. This is the speed of a string or a thin wire. Constructive. The path length is an integer times wavelength. Destructive. Path length is a half a wavelength. 3 halves, 5 halves, da 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 da. And then beats. Thank you. Thanks for